My name is Vanhger, and today I will talk about a topic which is not relevant to Stack and Circle Stack and FRI. Yeah, actually, my topic is my paper is about Nova, which is a recursive zero knowledge argument. Yeah. And actually, in this paper is introduce a technique which is called IVC, incrementally verifiable computation, and this technique is based on folding scheme. Yeah, so today I will talk about folding scheme. Uh, yeah, uh, folding scheme in informally definition like is reduce the task of checking two instances into only one instance. So you can understand this like 2 to 1 reduction. So actually, currently there are many exist techniques like this, like some check protocol and split and fold. And so I will give an example like we have a function xq plus x plus 5. So a witness here like if we choose x equal to 3, so the instant that we want to in this equation is the output of this function with x equal to 3. So is the instant here is 35. So folding scheme is if you want to check that the instant here is satisfies the function with the witness equal to 3, and so the task of checking 2 instant like this now reduced have only one task. So in the paper the authors construct a folding scheme over R1CS, which is a popular algebraic representation. So I will first talk about this. So here is R1CS. So take this an example. If we transform it into the into gates like multiplication gates, we have like I mentioned here. So S1 equal to x multiply x, and S2 equal to S1. To S1 S. So S3 equal to this one. So S2 plus X. So but in our set it defined in the multiplication gate. So I will make it to the multiplication like multiply 1. Yeah. So and our instant here x big X is equal to S3 plus 5 and multiply 1. So in R1CS they define a structure including 3 matrices. Yeah. The first matrix is represents the left side of the equation here. So I call it A, and the second matrix represents the right side of the whole equations here, B, and the final matrix defines the answer of the result of all equations. So I call it C, the C matrix. And so if the instant satisfies the equation with the witness like W here, the conditional equation is like A Z I V Z equal to C Z where I'm sorry. C the witness, the instant, and number one. So it's the definition of R1CS. However, in the paper, the authors construct the Foley scheme not over the R1CS, but the variant of R1CS. We call it Foley scheme over the committed relaxed R1CS. So I will introduce relaxed R1CS. So basically, our relaxed R1CS so include three matrices ABC like this. But it also include an arrow vector E, and now instead of using number one, it's use a scalar U. So the equation here turn into like IEZ like VZ equal to C plus E, where Z equal to W X and U. So here is relaxed R1CS, and finally the committed realized R1CS. So it's like equal to relaxed R1CS plus with additively homomorphic complement scheme. So in this paper, the additively homomorphic complement scheme the author used is Peterson. Complement scheme. So I will write it. So here is instant that we need to check in this relaxed R1CS. Here is a commitment of E. I will write E with the bar here. The scalar U, the commitment of the witness, and the big X public input output. And here now the witness, because we need to include the witness of the Peterson commitment scheme in here, so the witness now turn into the arrow vector is the witness of commitment of E, small r E W, and yeah. And now the conditional equation now turn into like this one, like E, commitment of E equal to the commitment of E and RE, and commitment of W equal to commitment of W and RW. And then the final equation like AZ, BZ, oh sorry, equal to U CZ plus E. Here is a computed realized R1CS. Oh, I'm missing scalar U in here. So, yeah. So now,
I have one question.
okay.
When it comes to the error term, I understand why it's using relaxed R1CS, but what about the scalar? What is the difference between why we add the scalar and the error?
Yeah, from my point of view, there's a scalar here. Now we don't use the number one here, but we turn it into the the general number. So I think we can use the scalar U for this.
But what makes using a scalar rather than one? What makes the circuit more relaxed? Can it accept more?
Yeah, actually, if you want to use a constant in the circuit, right? So for example, the constant is phi, so you need to, if you use one here, you need to a circuit like phi multiplied by one, which one is here. So you need a gate to do that. But if you use u here, the scalar u here, you can make u like phi, so you don't need a circuit here for compute the constant.
Interesting. Okay. So it's mostly for computing constants.
Yeah. So basically about it. Okay. So now I will talk about how we can, oh, time up. I think it's about 5 minutes. Is this okay? Yeah, okay. So thank you. So I will have a quick. So okay, it's coding scheme. Over the computed relaxed R1CS here. So I'm sorry. Let me see. Okay, so now we have two instances, like Z1 and Z2. So two witnesses correspond to two instances, like this. E1, E1, W1, and W1. So E2, E2, W1, and W2, and W2. So here, if we want to compile two instant, compile the task of checking two instant into what? The task of checking one instant, the directly way is using random linear combination. Yeah, so I will do this in here, like we have new u equal to u1 plus in u2. So z is also like that. But the error vector e is different, quite different. We use e1 plus t and to square e2. So t is new element here, so t is equal to c1 by bz2 and bz2 bz1 and substitute u1 cz2 and c1. So here, if we want, if you check to, so I will write the final equation here, like this. Az plus bz multiplied bz equal to. So z here we turn into like this one. And z2 z2 yeah, so equal to az1 bz1, right, of az1 bz2 plus az2 bz1, and this equation like az2 bz2. So if we keep continuing transform it, we turn into like so yeah, u1 plus u2 equal to c here, and c1 2 plus e here, and finally it equal to the uc z plus e. So it still hold the conditional equation here. So basically it's a Fourier scheme over the relaxed R1CS. So yeah, that's all. Thank you.